Okay, so welcome to my first stream, guys. So, what's the plan? I was going through this course, Build a Modern Computer from First Principles from Nand2Tetris, and I have already completed 2 weeks, and, and I also recorded the project sections of first week and second week, which included Boolean logic and Boolean arithmetic. So I recorded those videos, but as they were so long and it took a lot of time to edit them, so I thought from week 3 let's just start streaming directly. So that's the plan for this stream, and tell you a bit about this course. In this course we are basically going to build a modern computer from scratch using NAND gate, and this is the first part of this course, and there's also a second part, and I guess this part doesn't include the Tetris part, but let's check it out. So this part includes up to the assembler only, and I have already completed in total 3 weeks. So for this streams I'm going to record only the project sections. Now I'm not going to record me going through all these videos. So for this stream particularly, so for in first week I built all these basic chips, Nand not. Okay, so Nand was basically given, but I built not and or XOR mux and all these kits. And so one more thing about this course, we don't have to make the physical, I mean the hardware of these chips. We are going to use a simulator to simulate all this logic for these gates. And for week 2 I built half adder, full adder, incrementer and ALU basically. So for this stream we are going to start with the project 3. It contains memory, and we are given the data filter. So let me first start the hardware simulator provided by the course. So this is the hardware simulator provided by the course. So we don't have to tell this data flip-flop. We are basically given this flip-flop, and we have to build all this remaining chips from this primitive data flip-flop, and all the basic gates I built in project 1 and project 2. So let's just get started with building the first chip, which is bit. So let me tell you a bit about how this simulator works. So basically we have to load this kind of scripts which are called HDL scripts into the simulator to run the program. Let me show you the chip that I already made. Let's load Nand chip first. So this is the chip that I made in project section 1, and as you can see, the script has been loaded. And now to run this chip, we can first provide input over here, this input chain chips. So let's give A1 and B1 as well. Now we can click this button evolve, and it will give us the output for this AND gate, which is one for A and B both of them. So that's basically it for this simulator. So now let's get started with building this first gate, which is bit. So by the way, I don't know how to make all these gates, and this is the first time I'm going through this course. So that's basically it. So what is bit? Bit is basically a 1-bit register. It stores 1-bit value. So this is the logic of that 1-bit. It says that if a load bit is 1, this load bit is 1, then we provide the output the same input as t. Output t plus 1 will be input of t, and if the load bit is 0, then the output will remain same as the previous input at time t, right? Yeah, so if load bit is 1, then the output will be the whatever the input was at time t. Output will be at t plus 1 time of t time, and when we provide load bit as 0, then the output will remain the same as the previous out. So it will store this value, whatever was stored when the load bit was 1. So as per the description, we are given data flip-flop. So let's figure out how to load this chip inside our file. When a chip is given, it means that it is inside the built-in chips. So these are the built-in chips. Where is the DFF script? Okay, this is the DFF script. By the way, these are the slides from this videos, so I will be referring it. So this is how we have to build this 1-bit register. We need a DFF chip and a mux. As I said already, we have built the mux inside the project section 2. No, it was inside project section 1, I guess. This is what it was inside project section 1. So let's see. So let's first load. Let's first load the mux. I will have to check out what are the inputs of mux are like. So mux has 3 inputs and 1 output. So for first input, we will provide this input bit. A is this one, so we will provide this in. For B, we will provide, we want this output. By the way, can we directly write output like this? Let's see. And the selected bit will be same as load according to this diagram. This is okay. We also want the output bit as well. Output bit of the mux will be okay. We have to put the output bit inside an intermediate variable. So let's call it n1. So that's the part about mux, and let's load DFF as well. Let's check how this DFF look like. DFF just contains one input and one output. For the input bit, we will give this M1, and for output, so this script looks fine. According to this diagram, the script seems correct, but I don't know how it will use this time bit inside the script. Okay, let's try to load the script and see if it gives any error or not. It is giving us error. We can't connect gates output. Okay, so basically it is saying that we can't use this output bit inside this input. How are we supposed to get this bit over here? Let's check if they have provided any hints. They're saying that it can be built from a DFF and multiplex. Yeah, that's what we have done. We have used a multiplexer and a DFF. But then how are we supposed to take care of this time bit t plus 1 and t? As per the simulator, we can't use output directly inside this input. Plus 1 output equal to t plus 1. Okay, according to the comments, output bit is an array. But is it? I don't think so. It is just one bit, I guess. We can't use this output variable here directly. Okay, let's try to load this DFF, the DFF chip which we are already given. It should be inside this directly tools, built-in chips and DFF. Let me give input one. Okay, this is in decimal format, so we can give something like 30 as well. Value doesn't match the pins width. What does it mean? Okay, it is only one bit, so okay, we have to keep the format as binary, I guess. So we have loaded one inside this input pin. We loaded the DFF. Okay. We have loaded one inside this DFF, and now we can start the clock cycle by clicking on this button. So as you can see, it changed from 0 to 0 plus 1, but the clock cycle hasn't completed yet, so we have to click it 2 times. Now the clock cycle is completed and we have output over here, input and output, and it will store this value for all the clock cycle. You can also click on this button and which will, okay, the same illegal command send clock is already up. Okay, now we can run it, I guess. So as you can see, the value persists throughout this clock cycle. So that's the basic operation of DFF chip. But now we have to use this DFF chip inside our 1-bit register. But I don't know how to use it. Let's check the test script. So test scripts are basically a script which provides all the input and output. So for different values of input and output, we don't have to provide it manually. It goes through this test script and it runs for all of these inputs. Can't use output over here, so how do we implement the box there? What should we do? All the people watching, if you have any idea how to implement this, please comment. Suppose we provide a true. It's saying whether okay, it's saying that we can't connect its output pin to part. Can't connect this output pin to this part. If you can't connect the output pin to its part, then how are we going to create this loop? Is equal to m1. What if we use an intermediate variable for the second bit as well? Suppose we use a variable named v1 and provide it over here, and also provide this output to be v1. Okay, let's try to use it. So first of all, we have to create a variable. To get a variable, so let me write down what I want to do. What I want is basically a variable. Let's say it is called v1, which is either 0 or it is false initially, and we provide this v1 to this multiplexer, and we also provide this v1 variable to this output as well. So in that case, this the simulator won't give us errors, but first we have to figure out how to create this variable and provide the value false. So what we want is another chip which can basically pass whatever input we give it, which doesn't provide any logic, but just passes it through. Let me check if we have such a chip or not. And okay, what if we use the AND chip? Suppose if we were to use AND chip, then for AND chip, whenever both inputs are 0 0, we will have 0, and when both inputs are 1, we will have 1. So yes, we can use this engine as our pass-through gate. So let's use it. Let's load the AND gate. AND gate has a input as false initially, and the input will be also false initially, and output variable will go inside v1. So now we have this v1 variable which contains false inside it. False is basically 0 bit. Now we can use this variable inside this v1, and we can also give it over here v1. We don't let me open up the we don't only want this loop, but we also want this output as well. So we have to provide this v1 variable inside this output variable as well. So to get it, we can use AND gate again. So AND gate like this. A should be v1, B should be v1 as well, and output bit will be output. Okay, so according to our logic, this seems correct. Let's try to load it. It is giving us another error now. An internal pin may only be fed once. Is it saying? An internal pin may only be fed once by a parts output pin. On internal pin, may only be this hardware simulator is not made properly. We can't even read the whole error message. We have to rely on this tooltip, and sometimes it doesn't pop up. It's saying we can't use an internal by a parts output pin. Let me write down this error message. It is saying we can't use an internal pin. Okay, an internal pin may only be fed once by a parts output pin. Only be fed once by a parts output pin, which means an internal pin. Hey Rajesh, Rajesh, we are going through this course, build a modern computer from first principles. I'm going through this course, build a modern computer from first principles, and I've already gone through week 1 and week 2. and basically I'm streaming my whatever I'm making in this project sections. So I have already made all these chips, not and or and etc etc, and this chips as well, which were inside project 2. And now we are building project section 3. And right now I'm trying to build this bit chip. Bit chip is basically it stores whatever value was, whatever value we provide. It's at input. All right, where were we? Okay, an internal pin may only be fed once by a parts output pin. Internal pin, which is this one and this one, may only be fed once by a parts output pin. Output pin. What does it mean? Only be fed once by parts output pin. I guess it is giving error for this pin V1. It's saying we can't use V1 as the output pin. Output pin. Only be fed once, and we have fed it twice. Once over here and over here. So we can't do that, right? We can't use output pin V1 twice like this. Then what are we? How am I going to do this then? V1. Okay, let's store this output inside a different pin. Let's call it V2. But then we have to provide V2 over here as well. V2. V2. We also want, let me try to draw this diagram. It will be easier that way. Okay, so what we have done basically is we have provided one AND gate with two inputs and one output. We have called this output as V1. We are providing this V1 and mux. Okay, this is mux. first input is in and the selected bit is load. Okay, selected bit is low, and we also have this output of mux is inside M1, and we are passing this output to a DFF and the output goes inside V2, and we are also passing this output inside another AND twice, which provides it to this output. But we also want this output again inside this thing, so this V2 should go inside this mux again. That's what we have to figure out how to do. Kind of logic should go inside this diagram. This V2 and V1 should be similar according to the logic. If we use another AND gate and provide this V2 to V1, so basically what I mean is, if we do this something like this V2 which is coming out of this DFF, provide to another AND gate and provide it to this V1. I'm sure it is going to give us another set of errors. Let's just roll with it. Let's write it over here. We want another AND, and the first input will be V2, second will be the same. For the output, it should go inside V1. Let's try to load it again now. It is giving us the same error. Line number 21. Right, so we can't use this logic as well. We're supposed to simulate this time bit t plus 1 and t. Let's check out the slide. So what does clock tip mean? Should we use this kind of variable, clock tip? Chips. Should we use something like this, clocked in output? What does it say? Clocked chips include registers, RAM, devices, smarter and CPUs. The simulator knows that the loaded chip is clocked when one or more of its pins is declared clock. Okay, so we do have to use this clocked variable. Okay, so now should we declare clocked chips in only starting or at last? Built in the book. All clock chips are used directly or indirectly on many instances of built-in clocks. According to the diagrams, the clock chips are at the last. So let's try to initiate time at the last. Use locked input, and should we also clock the load bit? Guess not. Input pin doesn't need to be clocked, right? We are only providing it one time. And one is okay, we have to use, we can directly use this output variable over here. Let's try to run this code now. It is saying a gate class name is expected. A gate class name is expected. Get 23. So we can't use an intermediate variable. Okay. And we won't use an intermediate variable. We will directly use, we can directly use this. Let's remove it from the clock chips. This giving us the same error. What does it mean? We can't use gate class name. It is expected a gate class. Why is it expecting a gate class? Let me try to remove this command, this code, and let's run it without that code. V1 has no source pin. Where is V1? It's over here. Alright. We don't have source pin because we are not giving it anything over here. V1 has no source pin. Line number 25. We don't even have this line number 25. Don't have line number 25 inside our script. It is still giving us an error that we have an error on line number 25. Whatever. Seems harder to build this script. If we don't have to use this clocked code because it is already inside the DFF script, right? What if we write something like this? D directly provide input over here, and but we have to use V1. What does it mean when a variable is clocked? Let's try to run that chip. Provide one, and one clock cycle gives us the output. Tick tock, tick tock. It says here repeat tick tock, tick tock. Tick tock basically means two, one whole clock cycle. Tick and tock. Built-in chip. Alright, so clock timing for the next clock cycle. This goes inside itself, creates a loop. Right. So we already have a loop inside the DFF. We have this loop. Input, output, input, output, input, output. First attempt, provide the input directly. We can't provide the input directly because we also want to change the inputs. Provide output side M1 and this M1 can we create a loop like this? In and out is equal to 1, is equal to 1, that is equal to load. Yes, it is a big question mark for us right now. How do we provide the output back to input? Implementation of clock chip is based on sequential logic. The operation of clock chip is regulated by a master clock signal. So tick-tock is basically this tick and tock, right? Tick and tock. In our jargon, a clock cycle is equal to tick phase, this low phase, and tock, which is this high phase. And during a tick-tock, the internal states of all the clock chips are allowed to change. Their outputs are latched. What does that mean? The internal states of all the clock chips. At the beginning of the next tick, the output of all the clock chips in the architecture commit to the new values. On the next cycle, the output of all clock chips commit to the new values. Okay, so simulate clock chip cycle. The simulator knows that the clock chip loaded chip is clocked when one or more of its pins is declared clock, or one or more of its part or subparts recursively is a clocked chip. Does it mean subparts, parts or subparts recursively? We want the load to be clocked and this input also. The hint to implement this lies somewhere around these points. And these 2 points seems important to me. During the clock cycle, the internal states of all the clock chips are allowed to change. Internal states are allowed to change, but their outputs are latched. Latched means whatever was inside that particular output at time is equal to t will be the same for the time is equal to t plus 1 and so on until and unless we load new values. So for our DFF we have input pin as latched. Input pin is latched. It means can't change during this cycle. One tick and talk. But shouldn't the output bit should be latched? Let's try to see how this built-in 1-bit register works. If we provide 1 as the input and if we click the tick and talk, nothing happens because we are not providing the load instruction. But if we provide the loading instruction and now if we do tick and talk, we have the output. Inside this bit, in and load are clocked. But that's what I said earlier, that in and load will be clocked. That's given, but let's start to write. Let's provide load as the clock input and we are confused regarding this. No. Let's check what we are sure of first of all. Okay, we are sure that we want this input inside mux, so that's what we have given over here. Input inside the first input of mux, and we are also sure that this BFF should have the output of mux. So whatever will be the output of mux, we have to provide it inside the DFF. This is a problem. Maybe it is not. Suppose provide M1 over here. Now I have to take care of this second input of mux. Now currently we have provided M1 as the second input, which comes from mux itself. Right? Shouldn't be from mux itself. It should come from this output M1. We have to use another variable over here. Let's call it V1. And it should be over here. V1. External date class name is expected. Or we can't use this clock instruction or what? Alright, let's comment it out. Let's check what kind of error it gives now. Oh wait, it is not giving us any error now. Cool, let's try to run it then. Oh great, it is working. Oh wait, it failed at line number 9. Set input is equal to 0. Where did it fail? So if we set input as 0, load as 0, and if we tick, check the output, and top, check the output, it was correct. We set input as 0 and we give load bit as 1. We tick and top, we do get the output. So the load operation is working perfectly. Now if we provide 1 as the input and 0 as the load input, and we do tick and top, then of course it's not going to do anything because the load bit is 0. Now if we set the load bit as 1, it seems to be not loading the output, right? For 0 1 0 1 0 plus 2 0. Okay, so load instruction is not working. 2 plus 3 0 1 0, so the output remains 0. Okay, wait, we are not providing this out anything to this output. Wait, yeah, we have to provide something to this output. Right. We can use this AND gate. Output will be M1. So if we use AND and provide M1 over here and over here as well, and this should be the output. Let's try to load it now. Thankfully it doesn't give us any errors. Okay, it seems to be providing the output, but it is also providing the output. Wait, it is working correctly. Why is it giving us error? Okay, according to the compile script, at 3 we should be having 0 as the output. So we are getting 1. So regardless of this load bit, we are getting the input as output. So there's something wrong inside this mux. Let me try to let's create a new chart. So what we have is something like this. We have a mux. This is mux, let's say. We are providing two inputs. First input is in. Second input is M1. And we have a selected bit as load. And the output goes inside V1. Now this V1 goes inside DFF. And the output goes inside M1. Now we are providing this M1 to the AND gate, which passes it to the output bit. So what is happening is it is providing, our implementation is providing output regardless of the load bit. So regardless of the load bit, we are having the output over here. Regardless of this load bit, we are having output over here. So input is 1. Right. Okay. So this M1 is connected, isn't it? If load bit is 0, then only it should provide this input to DFF. it is 1, it should provide M1, which in our case it is not doing. Is providing the input. Declare M1 as clocked. We can't do that. Let's try to do it manually. If we provide, let's first provide 0 as the, if we do tick and talk, nothing should be changed. That's correct. But if we provide load as 1, tick and talk, things should be changed again because the input is 0. Now if we provide 1 is the input, we do tick and talk, it is not providing this 1 bit inside M1 as well as V1 as well as output. So let's try to debug. If we provide 1 1 as the input, 1 and 1, this input as 1 and load bit as 1, B is equal to M, whatever it was, then we should get 1 inside this V1 internal P. We are not getting 1 inside this internal pin. That means what? That it should at least provide us 1 inside V1. M B is equal to M1. What if we provide 0 now? Oh wait, if we provide 0, this bit changed. We provided 0, we get output inside V1, and we also get the output inside output, but it is happening on the next clock cycle. This is happening on the next clock cycle. Let's try to run it again. 0 0. We provide 1 as the input, then and if we click TikTok, nothing happens. Now if we provide 1 and we do tick and talk, nothing seems to happen. Tick and talk, nothing seems to happen. So what it is trying to do is wait, have we got it backward? Yeah, I guess we have got it backward. We have to provide M1 as the first input. And input should be over here. Let's try to run this code. Let's load the script. Great, it seems to be working. Let it load fully. Wait, why do we have this many inputs? Shouldn't only 5 or 6 inputs are sufficient? Is it going to loop forever or what? It's alright, let it run. It isn't even halfway there. It's probably going to run for 100 clock cycles, I guess. While it runs, let's clean up the script. All right, so it has completed finally, and it seems to be working perfectly. All right, so finally after how many, after 1 hour and 40 minutes, we have got our 1-bit register working. And I guess all the other chips will be relatively easier. A register will be basically a combination of 1-bit one 16 1-bit register 16 1-bit registers. So let's try to implement that now. Let's open up the register script. Now to load the register, and now we can directly use this 1-bit register inside our register. Let me first try to write down will be the functionality of register will be like. So we will have 16 inputs. We have an array basically of 16-bit, and all the single bits should go inside a 1-bit register. Let's try to draw the diagram. So what we want is basically something like this. We have a 1-bit register, bit. We want 16 of those. So 16 of those, and each and every 1-bit register will have one input. Let me open up the HDL of bit for the reference. So we have input and load. And we have one load. Now this load bit is same for all these inputs, so it will be similar, which will be the load bit we are giving to this register, and all of this register will be providing the output. Okay, so all we have to do is create 16 of this 1-bit registers. Let's get 1-bit register now. For the in, we have to provide the 0th bit, and load will be the load. Output should go inside output 0. Right. Now we want 16 of this. Two, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and 16. Alright, we have got 16 registers. This will be 1. Same over here. replace my internet seems to be lagging because I'm running all the streams simultaneously. Find it, replace and we 0 with 2. 4. 5. 6. 7. 8. 9. 10. 11. 12. 13. 14. And the last one, 15. Cool, let's try to run it. Register. Thank God it is not giving us any errors. Let's also load the test script. Oh damn, this test script also contains so many number of inputs. Let's try to run it. So far so good. That means this is our implementation of register bit also. Register chip is also correct. So yeah, I was right. This was relatively very easy. While it is running, let's check which one is the next chip. RAM 8. So the next chip is RAM 8. RAM 8. Let's figure out how to implement RAM at all. When this script is running, this is RAM, so also RAM will be also somewhat similar, but we will have to use other chips also inside this implementation. So RAM 8 will be basically 8 registers connected together. But now we also have to provide the functionality of selecting any of this register based on this address bit. Let me close this register HDL file. We want HDL file of RAM 8. Let's also open up the HDL file of register for the reference. Register.hdl. So let's open up a new canvas and let's try to draw RAM 8. So it is clear that we need a register. This is one register and it will have, we have a 16-bit input. This is 16-bit input. This input should go inside all of this. We want 8 of these registers in one column. And all of these registers will also have a load bit. Okay, so the script has ran successfully. So we have a register chip as well. Okay, let's continue with this diagram. What we want is this input should go inside all of these registers, but the state should only change when the corresponding address bit is selected. Address is also 3-bit. It is 3-bit because log of RAM 8 means we have 8 registers in total. So log of 8 base 2 is 3. So we have 3-bit address. So it will be something like this. Address bit will start from 000. So 000 means basically select the first register, and 001 second register, and so on up to 111, which will be the last register. And for this functionality, to select a register, we can use a multiplexer. This is with the implementation of RAM on 41 slide. Eight register RAM. So according to the tips given, what they are saying is feed in the input value to all the registers simultaneously. Of course, we are going to do that. Feed all the input to registers simultaneously. And use demux and mux chips to select the register specified by the address. Dmux and mux. Let's open up the slides for Dmux. Multiplex or mux basically have two inputs, A and B, one selector bit, and out that we have 3-bit input. So we want 3-way mux. – 16-bit 4-way mux. We do need a 16-bit mux, but we need it in total 8-way, right? 8-way, because we have 8 registers in total. So what we want is a 16-bit 8-way multiplexer to get the output. Let me check what kind of registers, built-in register we have. These are all the built-in registers. We have to use 16-bit mux, so way 16. So out of this 5 mux, we have to choose one. It's not 5. These are only 1, 2, and 3. 8-way. So we can use this mux 8-way 16-bit. This 8. So let's draw it. We only have one input, so we have to use the Dmux first. We have to use the Dmux. This will be the Dmux. It will have one input, one 16-bit input, and in total 8 outputs. And so it will just one address input, which will be of 3-bit address. So according to this address bit, it will output this input to the corresponding register. Now the register will have the input, and this register should also, we can use the multiplexer over here. This multiplexer will have all of the outputs from these registers. It will also have the address. It will be the same as this address, and it will give the output into output variable. Okay, the implementation seems correct. Let's try to write the code for the same. Let's first get Dmux. We want 16-bit 8-way. Wait, why don't we have a 16-bit Dmux? We only have 1-bit Dmuxes. Dmux. It's only 1 bit, but we want 16-bit Dmux. Do we have to create our own Dmux? Or should we directly use 16 demuxes? 61-bit demux. Let me check if I implemented a 16-bit demux in the project section. Didn't. I didn't implement a 16-bit demux, but and it is also not given inside the built-in chips. Then how are we supposed to do it then? Do we have to create our own demux? Check the implementation of 16-bit mux. Mux 4way16H2. We have to do the same thing for the demux. We want 8 demux. Let's write it directly over here. Demux demux 8. So let's use it. We have demux 8way. What does a demux 8way looks like? What does a demux 8way looks like? Demux 8way HDL. It has one input bit, one selected bit, and 8 different outputs. It should be something like this. Input is equal to input 0 and selected bit will be the same as Tetris, and output A should be R1. R1, and we want 8 of this. Let's copy it. 1, 2, 3, 4, 5, 6, 7. There will be one more. Let's call this 0. And this will be three, four, five, six, 7. 7. I'm sure there is a better way to replace all these values, but we are just going to go with our manual approach. Okay, so we have our own implementation of 16-bit 8-way debux. We have this outputs inside different intermediate variable. Oh wait, we have to wait. Provide 8 outputs to the same. Let's again change the implementation of it. Why can't we directly provide this inputs to all these corresponding registers and get rid of this box? And apply the logic of selecting the register on this load bit. So we only change the load bit according to this address. That way we don't have to have this 16-bit. So let me try to draw what I'm trying to say. So suppose we implement something like this. We have a register, 8 register, same as first figure. Now this input which is of 16-bit, what if we provide it directly to all these registers and apply the selector logic? Suppose this is demux. The input will be the load bit, and select this. We like something like this. It should be over here, but okay, whatever. And the address bit will go over here, 1 bit, 2 bits. Okay. If we use this implementation, then we don't have to have this 16-bit demux. Correct. We can bypass this thing. Can directly use our demux 8-way. The input, by the way, demux 8-way is of 1 bit, so this should be the load bit. The input should be the load bit. Selector will remain same, which will be address, and output. Let me check what does the demux 8-way look like. Okay, this is how it looks like. A, B, C, D, E, F, G. Suppose if I write something like this, B will be R1, D will be R2 and D will be R3. C will be R4. F will be R5. G will be R6. G, H, the last one, H will be R7. Right. We have this individual outputs. We have load. Now we need 8 registers. We need 8 registers. Register as 116-bit input, so this will be the same as the input, and load bit for the first register. The load bit will be R0 and the output will go inside. Okay, we have still to figure out, we are yet to figure out how to provide these outputs. Okay, we directly, this implementation is correct for the output, so we can directly provide something like this to the mux, and this will be the output and address. And as we already have the mux, where do we store this values? Let me open up the mux as well. We want 8-way 16. 8-way 16, that means it will have 8 inputs which will be of 16-bit. 8 inputs. We have to provide mux 8 inputs. Okay, this out. So let's call it RO0. This will be the first register. Let's copy it. We want 8 of this. 1, 2, 3, 4, 5, 6, and 7. The input will remain same for all of this, but we have to change the load bit and output bit. This will be 2. This will be 3. Four, 5, 6, and 7. Good. And we have this logic and this logic. All we have to do is provide all of this outputs to this multiplexer. Let's do that. we want mux 8-way 16, and for A we will have RO0, B will be RO1, C will be RO2, D will be RO3, E will be RO4, F will be R5, G will be RO6, the last one H will be RO7. Great. Okay, we also want the selector bit. Selector bit will be the same as the address bit, and the output will go directly into output. Let's try to load the script. RAM 8. Mux 8-way-16 is not found in the working and built-in folder. Mux 8-way-16. Why is it not found? Okay, we have to capitalize W. Okay. This should be capital W. Now it will load up. What is it saying now? Add has no source pin. On line number 30. Okay, it should be address, not add. Address. Same goes for the selector bit. Should be address. Okay, it has loaded successfully. Let's try to run the test script now. RAM 8. Our implementation of RAM chip is working very, very slowly. But I don't see any other way right now, any other optimized way. This seems like the best possible case. And of course it is going to take time because it is not running inside the real hardware, but our program is just simulating a RAM. It looks beautiful when it is changing the specs. While it is running, let's try to figure out how to implement other chip, which is RAM 64. RAM 64. 64. It will be basically 8 RAMs stacked together. 8 8s are 64. Now do we stack them together? Let me close the script. RAM 64 isn't inside this folder. We have to go inside another folder. Inside this 64. We also have to. Oh, it will be later. Where is 64? RAM 64. Okay, it is inside A as A only. Okay, damn. 64. So for the RAM 64, we have the same number of inputs. One input, 16-bit input, load, address, and out. All we have to do is, let's try to draw. Cool, our script has ended as well, and it ran successfully without any errors. So our implementation of RAM 8 is correct as well. Let's continue RAM 64. By the way, I'm creating new canvases for different figures, and I'm not trying to rub it on the same canvas because apparently when I try to select and rub delete the picture, this program, which is Xpaint, crashes. So I have to create new canvases for different diagrams. Alright, so to implement RAM64, we want a simple RAM first of all. RAM 8 and RAM 8 RAM 8 has one input which is of 16-bit and load and address. It's just the same for RAM64. So we can apply the same logic. We can use 8 of this RAM and we can directly provide 16-bit input to our RAMs, and now we have to keep in mind this addresses as well, and the loads, and this load and this addresses. Right, it is too much confusing. This load is basically okay, not load, this address will basically select any of this RAMs. So each and every RAM will contain this address input. This RAM has an address input and a load. And this address is of 3-bit and this addresses are of 6-bit. So okay, this address selects the one of the register inside this RAM. This address selects one of these RAMs. So this 6-bit address looks like this. This is a 6-bit address which we are going to give to this RAM64. Now we have to select any of this RAM bit using this logic. Alright, so if we use three of these bits to select one of the RAM, zero 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 will select first one, 1 1 1 1 1 will select the last one. load is 1. Alright, so I guess I'm going to end this stream here, and I will continue for the next part from here onwards. It's 9:30 on, so I have to get dinner now. So alright guys, so this is it for this stream. I will see you soon again. Maybe later after I had dinner. I don't know, maybe later, maybe tomorrow. So see you soon then.